All right, and here we are. Welcome to part two of Bitzer's refrigeration series. We are once again joined by Phil Boudreau. He is 37 years experience working in the HVAC industry, primarily specializing in refrigeration. Now, if you attended the first one, that was last year. He went through kind of the opening spectrum of refrigeration. This time we're tackling subcritical CO2 compressors and cycles with a little introduction to transcritical compressors, which we're going to cover in February. That's a lot of intro. Phil, why don't you join us here and show your face again? There he is, and he's on mute, which is a Zoom staple.
There's proof that I am here.
There's proof that you're here. Phil, thank you so much for coming back. This is part two of your three-part series. We've got a lot to cover, a lot of great information. So I'm going to throw to you, and I will return at the end to lead the Q&A.
Absolutely. And don't we always have lots to cover? Good morning, good afternoon, everyone. Thank you for attending. So as Matthew mentioned, today's topic will be subcritical CO2 refrigeration. And we will be covering transcritical on February 16th, and that's more of a lengthy topic. So I took the transcritical compressors out and popped them into the subcritical side here. So it wasn't meant to be confusing, but that's why it was done this way. So initially, we're going to take a look at some CO2 compressor technology, again, subcritical and transcritical compressors. What makes these compressors different than HFC compressors? Subcritical CO2 refrigeration, what is it? What does it mean? And also we'll take a look at some subcritical layout examples. Back to compressors. First of all, it's important to understand that just generally speaking, there are challenges when using CO2 as a refrigerant. For example, most of us, I'm sure, know that CO2 exhibits high pressures, quite high pressures compared to a lot of the refrigerants we're used to working with. High suction densities, high miscibility with oil, which is often a challenge. Even with HFC refrigerants and POE oils, we had a fairly high miscibility situation there, but with CO2 and POE oil, it's even more challenging. Strong degassing effect. So strong degassing takes place when you have a sudden pressure reduction, and this is your refrigerant is degassing out of the oil. And the consequence of this is foaming. And foaming doesn't do a great job of lubricating the compressor. So we want to do whatever we can to prevent this from occurring. And boundary friction, which is a consequence of not adapting a compressor and lubricants when we have high pressures and high densities, and we have a very miscible refrigerant oil combination, we can run into situations with boundary friction where the parts are lubricated, but they're almost making contact there. So that's another challenge. So the drive gear, or the running gear, if you will, of the compressor needs to be suitable for this. Oils need to be chosen to be appropriate. Superheats need to be determined for achieving good long-term compressor operation. We'll talk about some of these operating limits later on in the presentation. So first and foremost, the CO2 compressors, the Bitzer CO2 compressors, are based on the Ecoline Octagon series that many of us are familiar with. The Octagon series use a 4-pole motor, so it turns at 1750 RPM, has a VFD capable motor. Just with all Bitzer compressors that have motors in them, they're VFD capable. Of course, have a drive gear optimized for CO2. The smaller compressors, the 2 and 4 cylinder, use the centrifugal lubrication system, which features the dynamic disc to transport oil from the crankcase up into the crankshaft area, and from there into the various other areas, sections of the compressor. And then, of course, with the larger models, the 6 and 8 cylinders, these require an oil pump, since the oil basically has a much longer way to go. The castings themselves have to be able to withstand higher pressures as well. So subcritical, we have those, and then there's the transcritical, which of course would require even high pressure ratings, and we'll talk about what these pressure ratings are, just to give you an idea. CO2 applications, involving Bitzer compressors also require special oils. So as I said before, POE oil and CO2 has a very high miscibility. So one of the ways in which to mitigate this is to start out with a higher base viscosity, because we know there's going to be more CO2 that's in that oil at any given point in time. So basically these oils that you see here are higher viscosity. So we have one oil, which is considered the standard oil, which is for subcritical compressors, say in a cascade circuit where the condensing temperature is also subcritical. I know, whatever that means, right? We'll get to that shortly. Then there's the BSE 85, which is also used in subcritical compressors, but used in transcritical compressors. So in your, for example, supermarket type booster systems, BSE 85K would be your standard oil. And then getting into the higher temperature applications, for example, heat pumps and what have you, once we cross a certain threshold in terms of pressures and temperatures, then these would require the use of the BSG 68. So here's a quick glance at what the compressors look like. Very similar to the HFC compressors, just obviously much higher pressure castings. And I think that's quite evident with the photo of the image of the transcritical compressor here. Just to give you an idea of the range of the compressors on the subcritical side, two-cylinder compressors up to the largest four-cylinder compressor. Taking a look at ratings, I have just converted from the SI units to IP here. So if we look at an application operating minus 31 Fahrenheit saturated suction temperature, 23 degrees Fahrenheit saturated discharge temperature, which is approximately condensing temperature. You can see the range in capacities from 10.5 thousand BTUs up to 337,000 BTUs per hour. And for the operating temperature range, evaporating temperatures from minus 58 to plus 5. Don't forget the triple point, as we discussed back on before the holidays in the first session. The triple point is approximately minus 70 degrees Fahrenheit. So we couldn't go much lower than this anyways with a subcritical compressor. In terms of condensing, the low end would be minus 4 and then upwards to approximately 60 degrees Fahrenheit. So those are the standard subcritical compressors, but it's important to note that there is also a higher pressure version of the subcritical compressor, which is often used in basically in booster systems and I suppose other applications where higher standstill pressures are required. And I'll show you what these pressure ratings are. For now, we'll just take a look at the range. Again, approximately 11,000. And I made a mistake up here. This is this should be something like 65,000 BTUs or something up here. So you have that range in compressors, and of course, if you need capacity, more capacity rather, you need to use more compressors. And this is pretty typical of CO2 systems. Anyways, generally, more steps of capacity control that you have, the better. So the operating limits for the ME series look something like this. Again, minus 58 in terms of the lower end of the evaporating scale and plus 32 on the high side. 77 degrees Fahrenheit max condensing and minus 4 degrees Fahrenheit minimum condensing. So the standard SL models, we'll call them, we'll call them the lower pressure casting version of the subcritical compressors, have a low side rating of 435 PSIG and a high side rating of 770 PSIG. So again, the ME compressor series this is a higher standstill pressure capable compressor. So both the low side and the high side have pressure ratings of 1,450 PSIG. As I mentioned before, all of the Bitzer compressors using that have an integrated motor, so a semi-hermetic compressor, can utilize a VFD. It's optional. You use a VFD for capacity control. And in this case, the standard subcritical compressors from the 2 NSL up to the 4 NSL, which is the 4-cylinder, we'll say approximately 30 horsepower or so. 30 to 70 hertz is the standard range. And then with the ME series, 30 to 70 hertz. Okay, and every once in a while it comes up, well, can I operate just outside that range or what have you? Whenever you have a question about the viability or acceptability, if you will, of operating a compressor at different speed range, these are the general speed ranges and we shouldn't go out those outside those limits. If there are special applications, never just try it. Always contact Bitzer for Bitzer's advice on this. So the transcritical series compressors, as I mentioned, we will include with the subcritical compressors, and we have a range of approximately 33,000 up to 402,000. So this is basically a series of 2-cylinder, 4-cylinder, and 6-cylinder compressors, and operating approximately medium temp conditions. And you may notice that for the rating point here, it says there's 1,305 psia. So that is your pressure of the discharge, and 95 degrees Fahrenheit, TGCO, which is the temperature, the gas cooler outlet temperature. As I mentioned in the previous webinar that we did covering CO2 properties, once we operate CO2 as a supercritical fluid, there is no relationship between pressure and temperature, so we have to identify both. So the transcritical compressors were traditionally known as the TC models, and now Bitzer's introduced the TE models, which also enable us to apply unloading. So variable speed is an option using an unloading method in conjunction with an IQ module, which we did discuss in another webinar as well. We can cycle the unloaders to get some capacity control. So generally, you're going to cycle compressors. More compressors is generally better. Of course, more compressors takes up more space. There's a cost disadvantage, perhaps, but another way to fine tune your capacity control is either with a VFD or unloading, depending on the scenario and what the preference is. But the point is that the flexibility is there. You can go either way with it. And for the application limits for transcritical compressors, we can see them here, 580 psia, minimum discharge pressure up to close to 2,000 psi with the smaller models, and with the largest, the 6DTE, the one particular model is 1,885. So very high pressure range on the high side. And again, it's listed in pressure because there is no saturation temperature when we're running transcritical, so we have to establish the pressure and gas cooler outlet temperature. Evaporating range -4 up to +68 in both cases. And there is a larger model coming out. They just keep getting bigger. There's an 8-cylinder that has been introduced in Europe. That one is referred to as an 8FTE and the other is an 8CTE. These are basically larger displacement compressors. And just to give you an idea of the capacity, operating, we'll say medium temp applications. One is a 610,000 BTU compressor operating 60 hertz. And then the even larger one is 872,000 BTU. So IQ module ready, meaning that you have a module that can control all of the peripheral accessories on the compressor. That includes unloading, oil safeties, crankcase heater. The module knows when the compressor is running or not, so it knows when to bring the heater on, so forth. So greatly simplifies wiring, just as it does with the HFC compressors. For the pressure ratings of the transcritical compressors, note that on the low side, the pressure rating is 1,450 psi. And then on the high side, they have a rating of up to 2,320 psi. And in terms of speed ranges, we do have to be aware of, what model are we applying, and because the different compressors can have different speed ranges. So we never want to assume that, we can always apply the same speed range. Always check the software, consult with Bitzer to find out what the allowable speed range is. And you can see here, some compressors can operate, the 2-cylinder compressor, for example, we should only operate down to 30 hertz. And the rest of the other compressors, we can operate down to 25 hertz. and generally up to 65, 70, 75 hertz, again, depending on the model that we're talking about. One thing that is different with CO2 compressors is the fact that they're equipped with pressure relief valves. So the subcritical compressors, for example, have a pressure relief valve on the suction side, and this is to prevent casting overpressure. Okay, and then you have also on the transcritical compressors, there's a relief valve on those as well. And you're just looking at the version here that applies to North America. And just some notes about the relief valves. The only purpose of these relief valves is to protect the casting from overpressure, okay? So if somebody was to inadvertently isolate the compressor, leave the discharge service valve closed, and then start up the compressor, we talked about the pressure increase. The rate of pressure increase with CO2 is very high, and the relief valve needs to be there to protect the compressor in this case. For the relief valve that's on the suction of the subcritical compressors, note that the relief valve is only in the circuit when the compressor is isolated. So if there's CO2 trapped in there, compressor is isolated, temperature rises, pressure rises. If it does exceed the pressure rating of that casting, then that relief valve will open. But note that when the service valve is open, that the relief valve is no longer in the circuit. And on the transcritical side, that relief valve is always exposed to the discharge gallery that's just upstream of that. So this is after your cylinders, okay, and the valve plates, the discharge gallery, that area inside the compressor can vent through this relief valve in the event of an overpressure situation. So these relief valves, because they're there specifically to protect the compressor from overpressure, should never be used in lieu of system pressure relief devices. The flow rates of these relief valves are based on the size, the volume, the internal volume of the compressor, and not the system volume. So this is a very important point. And relief valves is always must be sized in accordance with the ASHRAE 15 safety standard for refrigeration system. And we should also refer to any local code and standard requirements that there are. And B52 code is another one standard. There's a lot of resources available for learning about the CO2 compressors, their sizes, their capabilities, their operating ranges, what have you. And you can find these in a series of brochures, operating instructions. And in the operating instructions, there's a lot more than just talking about operating the compressor itself. There's instructions on how to apply these compressors in systems safely and properly charging systems in the safest possible manner. We always want to avoid the possibility of forming dry ice in the system, creating any kind of dangerous situation. So generally, commissioning will take place in steps, and the operating instructions are very good about explaining what these steps are to give you a good general overview of how systems should be charged. Preventing CO2 release, things like that, how should piping connections be made, just a lot of information like that in these guides. So I do recommend having a look at them. And definitely you want to know the components, as always, about those components as much as you can before you even think about working on them. So this is a good source to find that type of thing. And there's software, of course, so you can simulate systems, or you can look up capacities for individual CO2 compressors. You can get their dimensions and weights and line size connections for your suction and discharge line, and so forth. So this brings us to subcritical refrigeration. What is subcritical refrigeration? Subcritical refrigeration is something we've been working with as an industry for many, many years. All it means is that your system is operating subcritically. So if you look at a pressure enthalpy diagram, here's our pressure scale, and then we have the enthalpy scale along the horizontal axis. Then we have a two-phase region enclosed by this dome. Okay, you may recall that the critical point is at the top, whenever we transcend the critical point, or once we pass the critical point of the refrigerant, then we'll of course be operating the refrigerant as a supercritical fluid, and the actual cycle becomes transcritical. Okay, so that's what we're going to be covering on the 16th. But with a subcritical system, your evaporation takes place in the evaporator subcritically. Then we compress the refrigerant using subcritical compressors here, and then we reject the heat subcritically because we're still below the critical point. Okay, so once that refrigerant is desuperheated, recondensed, and possibly even subcooled, depending on it's probably going to be subcooled anyways. Otherwise, you wouldn't have any, you'd have flash gas entering the metering device as soon as that liquid is exposed to any kind of pressure drop. But once the refrigerant returns to liquid, then we throttle it through a metering device and start the process all over again. So this process here is basically the same as any refrigeration air conditioning process using positive displacement compressors that we've seen in the past. Okay, and even so we're talking about scrolls and recips and screws, but for HFCs, HFOs, ammonia applications all operate subcritically. So we're very familiar with the process already. It's just understanding the nuances with using CO2 in subcritical systems. So just a few examples, and this isn't meant to be an exhaustive approach to showing the various subcritical cycles that you can use. These are just a few ideas of how CO2 has been and can be applied. So first, we're looking at basically it's a chiller. So here on the upper stage, we'll have an HFC compression circuit. It's basically we call it condensing unit. It's basically a chiller. It's a CO2 chiller. So we've got a compressor circuit up here, and the evaporator for that circuit is actually being used to recondense CO2 in a pumped CO2 circuit. So we have our compressors here discharging into a condenser, business as usual, desuperheat, condense, subcool, and then the liquid drains into a receiver where it can be then transferred to one or more expansion valves on the system. And this could be a brazed plate type heat exchanger that just operates at a temperature, of course, that's lower than the CO2 loop. And basically, this is a wet type of system here where you've got CO2 being pumped through with some balancing valves, pumped through the evaporators, absorbing heat, and some vapor is formed. And then again, this will allow that vapor to be recondensed. So this is very simplified, but this is one approach that can be used. So this will be called a receiver or liquid vapor separator. And then, of course, we have our circulation pumps down here. Another approach is typical of a cascade system. Now, this will be similar to if you're familiar with ultra low type systems that operate cascade. You have two compressor circuits, and you'll have generally two refrigerants, and one refrigerant will be more volatile than the other. As it turns out, it also happens to be a higher pressure. So, for example, on the low side, it would be something like a R23 or 508B or something like that, and then you would have it could have been 404 or 507 nowadays, perhaps 448, 449, something like that. And these two circuits are coupled by a heat exchanger. So what we're doing here is something similar, except we have a compressorized CO2 circuit to serve the low temp. So here's our compressors that discharge the heat into this heat exchanger, recondense the refrigerant. The liquid travels to the receiver. From the receiver, enters the expansion valves for the various low temperature evaporators, and where the evaporators can then absorb heat. So we're absorbing heat in the low temp side, and we have to think about all the sources of heat, because ultimately in a cascade system, your condenser on the high side of the high stage has to reject all heat that's been added to the entire system. So here we have the heat that's been added in the low temperature evaporators. We have the heat of compression, which is equivalent to the power input to the compressors. These will be rejected into this heat exchanger. And of course, any suction line heat that's picked up, all these sources of heat will be added and rejected at this heat exchanger. So this amount of heat is absorbed by the cooler side of the heat exchanger, which is connected to the higher stage compression circuit. Then that suction gas travels to the high stage compressors. Again, this could be a 134A system, 450A, it could be 513A, could be 448, 449. There's a number of refrigerants that could be used. Could be a hydrocarbon type circuit, in fact, if codes and standards will allow it. So again, we have this heat that was absorbed at the evaporator, the cascade heat exchanger, and then we have the heat of compression, the power input to the compressors, and all of this adds up to equal the total heat of rejection from the entire system. So you've got all of these sources of heat all add up to equal the total heat of rejection. Another possible layout is similar to what we just saw with the cascade circuit. And this is a cascade circuit. The only real difference here is that your high stage circuit, in addition to being coupled to the low stage, so it handles all of the heat from the low stage, it also serves medium temperature loads. So this could be a supermarket or any kind of application, in fact, where there are low temp and medium temp load requirements that need to be served. So the medium temperature compressors then will handle not only the heat absorbed by the medium temperature evaporators, but also the heat rejected by the low temperature system. But again, because these two circuits are coupled by a heat exchanger here, you've got two different refrigerants, and that's the main advantage of using a cascade system, is that you can break down stages to get the individual compression ratios lower and use different refrigerants that are more effective, more efficient, more appropriate. For example, the pressure range is more appropriate, so we're not operating the refrigerant in the vacuum, things like that. So it gives us a lot of flexibility. And some of the earlier CO2 systems, in fact, that were installed were cascade systems, and some are, I'm sure, are being installed today, and they look much like this. Next, we have a similar to what we saw on the previous slide, a form of cascade system. So again, our low temp, the heat rejection from the low temp circuit gets rejected into this heat exchanger here. It's condensed into the receiver. Now the difference is this is a pumped CO2. This is a pumped CO2 circuit here. Okay, instead of being a direct expansion as we saw in the previous slide. So the idea is just to point, like, these aren't the ways that things need to be done necessarily, but there's many different ways in which you can lay out system components and that to get a job done, depending on what the operating parameters requirements are for the system, depending on the sizes of the system. There's a lot of things to be considered there. For a pumped CO2 circuit, in order for this to work, obviously we need to have some liquid to feed the pump. So it'll look something like this. Up here, we have more or less a thermal siphon kind of arrangement, because as the liquid drops into a receiver, similar to an HFC system, as the liquid level fills, somehow the vapor needs to be able to vent back to your condenser. And that's basically what we're seeing here. So pipe sizing and the piping lengths are critical in that they need to ensure that the thermal siphon effect can actually occur here. Once we recondense the refrigerant and we have liquid available to the CO2 receiver, next thing is there's a drop leg that comes out of the receiver, which will generally be sized enough to make sure that the pumps aren't going to cavitate. So you've got a good liquid column above the pumps. Then these pumps are going to simply circulate CO2 liquid through the various evaporators in the system. But note that as the evaporators start satisfying, So they meet the load. So there's no longer a requirement for refrigeration. So the valve will close on that circuit. And as the valves close, what's happening is the pressure leaving the pump side is getting greater and greater and greater. So that would be the purpose of this relief valve. That's what they're showing here. The relief valve then would vent the excess back into the receiver. So it's available for any other evaporators that require refrigerant. A few notes on oil management here. So I extracted a portion of one of the drawings, and these drawings I obtained from my colleagues in Germany. They have a lot of great drawings and system layouts and resources to get this kind of information. And what I just wanted to show you here, there are some differences between the CO2 oil management systems, different compared to HFC systems. So the first thing is, of course, we need an oil separator. That's really not different. High efficiency oil separator is recommended. So this would be, I would say of the coalescing type to get the highest oil efficiency separation as possible. Next thing will be an oil solenoid. This is a little unconventional because those of you who know, for example, in the supermarket system where we use the low oil pressure management system, which is what this is, you have an oil separator, and then you have this is referred to as a low pressure oil reservoir. I just call it oil reservoir here, but we have a solenoid here. Why do we have a solenoid? Well, there are some parts missing here, some components. This again is a simplified drawing. Because due to the high pressures that we see in CO2 systems, having a float ball in the oil separator really isn't so practical. You're under very high pressure, and the purpose of the float is to lift once there's sufficient oil in the oil separator, and then allow that to return to the oil circuit, or in this case, into an oil reservoir. So instead, what's used is an oil separator that has, for example, an optical oil switch somewhere down low on the oil separator. So as the oil level accumulates in the oil separator, at some point, the optical switch is going to sense that there's oil there. And when it does sense that there's oil there, that's going to initiate a dump cycle, or transferring oil into the oil reservoir. So the optical switch on the side, which we don't see here, would say, hey, I've got oil. It would tell the solenoid to open, basically. And then the solenoid opens, allowing the oil to transfer into the oil reservoir. And then once the optical switch determines that there's no oil left, we've drained the oil out, we don't want to leave this valve open, so then that will close. So that's, at a high level, how this type of system works. Then there's a pressure reducing valve, and the purpose of the pressure reducing valve is to, instead of having full high side pressure oil enter the compressors where the oil level regulator opens and you're just shooting the oil into the compressors, the idea is to reduce the pressure and do a little bit of degassing of that oil. As I mentioned before, CO2 and POE oil can have some very strong degassing effects, especially when there's a lot of refrigerant in that oil. And generally speaking, the higher the pressure of the refrigerant, the more refrigerant's going to be in the oil. So if we can degas it before the oil enters the compressors, then there's an advantage to that for sure. And this has been done with low pressure oil management systems for many years. So what's actually happening here is this will be your medium temp. For example, this is part of a booster system, actually, which we'll be covering. We'll be taking a look at that on February 16th in more detail. We've got two circuits, and so this one is vented to the medium temp circuit. So what this valve does is it looks at the suction pressure of the medium temperature compressors, and depending on its setting, it'll be set for, say, maybe 20, 25, 30, 35 psi, higher than the suction header pressure. So that means that this oil reservoir will be held at a pressure that is several psi above the crankcase pressures of the compressor. So that enables the oil to travel from the oil level regulator, from the oil reservoir into the compressor whenever an oil level regulator determines that the oil level is low. If the pressure was the same, we wouldn't have any flow because there's no pressure difference to actually drive the flow into the compressor. And note that this regulator here is on the higher temp circuit. This being a low temp circuit down here, if we were to vent this chamber or this low pressure oil reservoir to the low temp suction, then the pressure of this tank or reservoir would be lower than the medium temp or the high stage compressors. So anytime those oil level regulators open on the higher stage compressors, oil, if anything, would want to travel out of the compressors and back up towards the reservoir. And of course, we don't want that. So that's at a high level, generally how the low pressure oil management system works. And here you can see other oil level regulators installed. We didn't show all the regulators here. This is just to give you an idea. This is actually showing an oil level regulator on parallel compression circuit on medium temp or high stage compressors. And then we have subcritical. But again, we'll talk more about parallel compression in the next session on February 16th. And it looks something like this. So we have a transcritical compressor. It doesn't really matter. It could be a subcritical compressor. This is a photo that I took of a training system in the training lab in Rottenburg, Germany, which I encourage you to have a look at anytime you get over there. It's really, really cool to see the system up and running. And what we have here is the compressor itself, of course. In this case, it's a transcritical compressor. Then we have an oil separator. The oil separator collects the oil to a point where the oil level is high enough with this optical type oil level sensing switch, determines that there's oil here. That will initiate a transfer of oil from this oil separator back to D, which would be our oil reservoir. And I'm sorry, I wasn't actually thinking of when I took this picture. It's just I think I was more focused on this area here, but you can just see the oil reservoir in the back. Okay, so this will be your oil reservoir that I just explained that's vented to suction pressure plus several psi, just so we have enough pressure differential to allow for oil to transfer into the compressor anytime the oil level regulator opens. And E, of course, is the oil level regulator itself. When this opens, this is going to open, of course, when the oil level is low in the compressor. It will open until the oil level in the compressor satisfies. Just a few words about operating conditions. It's always very important before any startups. Always understand the components that you're working with. In this case, the compressors. We have requirements, operating limits for these compressors, of course, and all compressors have this. But we never want to make the assumption that we've been doing this for many years with HFC systems. So I know what superheat is. I'll set the superheat on the CO2 system the same way. It's very much different because, like I said, the solubility of CO2 and POE are higher, more chance of strong degassing, which leads to oil foaming, which is never great at lubricating a compressor. So how do we prevent all this stuff? Well, superheats are critical. Generally speaking, your required superheats entering CO2 compressors are greater than with HFC compressors. And note here that achieving the minimum operating temperatures can be more challenging than keeping temperatures below the maximum limits. Specifically, what this means is superheat. And I'll give you an example. I think it's a couple of slides from now, just giving you a super high level overview of what you can run into with a CO2 system. That can be very challenging. We just have to find ways of mitigating it. There's always a way around it, but we have to be aware of these things so that the system can be designed correctly. So generally speaking, minimum suction superheat entering the compressor is 20 Kelvin or 36-degree Rankine. Okay. You can round that up to 40 degrees. It's no problem. You just don't want to operate at lower superheats here. Generally speaking, there is a caveat to this. Lower superheat is possible, but only when the minimum crankcase temperature and the discharge superheat are achieved. And any of you who have participated in past training seminars know that I talk about discharge superheat a lot, even with HFC systems. It's quite common out there that we see systems operating with low discharge superheat. And you can have a few degrees of superheat entering the compressor, but it may not be enough. The discharge superheat's got to be high enough. And with CO2, generally speaking, the numbers are higher. So minimum oil temperature before starting. Make sure those crankcase heaters are on. They should have that oil temperature warmed up sufficiently. For example, 20 Kelvin or 36 degree Rankine above the ambient temperature. And what this does is it limits the flow of refrigerant to, it prevents it to some extent to the oil, but never eliminates it. Okay, so it's important to understand that you're never going to eliminate refrigerant from getting in the oil. It's going to get there no matter what. And it's a function of oil temperature, the refrigerant type, the oil type, and the refrigerant pressure. And generally speaking, with that, the higher pressure refrigerant and the lower temperature of the oil, these two things work together to result in more and more refrigerant in the oil. And this is where we see things like foaming on startup, and we see it in HFC systems as well. It's foaming, and you've got an oil switch, whether it's optical or a differential pressure type, that can't develop pressure, or it can't see the oil. All it sees is foam. And then, of course, the timing sequence is initiated. And if we can't clear up that oil, by the time the timing has expired, then of course it's going to trip on oil failure. But the point is, we want to avoid this altogether, because every time we do this, we're running the compressor. We'll call it in an emergency situation, emergency running characteristics. The Bitzer compressors have this built into them, but you can't do this indefinitely. You will reduce the life of the compressor. Superheats are absolutely imperative with compressors in general. And I get asked the question, by the way, about crankcase heaters. If you have equipment indoors, do we need crankcase heaters on systems? Whether they're HFC systems or CO2 systems, absolutely. And you'll find in instructions that I think in the Bitzer instructions, if you're below a certain charge level in that, you could in theory get away with without a heater. I'm a big advocate for heaters. Generally speaking, you want to have crankcase heaters on the oil to limit the amount of refrigerant that's going to end up in that oil. So even if it's indoors, and I can think of an example where we had a medium temp rack, and I'm talking about an HFC example here for a moment. And it was an auxiliary contact on the compressor contactor failed. Well, it was intermittent. Sometimes it would work. So when the system controller took the compressor offline, the crankcase heater would come on. Other times it wouldn't. And it was a medium temp system. So every time the compressor would shut off, it could shut off for hours, it could shut off for days, maybe even weeks, depending on the rack controller and what it's calling for. And the longer it sits there without a crankcase heater on, especially with the higher pressures that we see in a medium temperature system, you're going to end up with more refrigerant in the oil. This is what becomes a problem. On startup, your oil has a viscosity that it's just way too low. Probably somewhere down around, it could be 5 centistokes or something, when we're generally working with viscosities in the compressor that are much higher to lubricate the bearings. So every time this is done, it just reduces the life of the compressor. Minimum oil during or oil temp during operation, 95 to 104 degrees Fahrenheit. This is your minimum oil temp, so it's going to be that or even higher. But certainly if you see a crankcase is freezing up and that's obviously your oil temperature is too low. And you may see oftentimes there's systems where you're running, your superheat is good at the evaporator and we're holding a stable superheat, and that's great. but just not always enough. Sometimes we have to add more heat somewhere in the form of a heat exchanger, and I'll show you an example of that. Absolute minimum discharge temperature is 122 degrees Fahrenheit. Oh, and discharge superheat for CO2. So that's 40 Kelvin or 72-degree Rankine for subcritical operation. And then in transcritical, obviously we can't talk about superheat because you're dealing with, the pressure and temperature are not related in the supercritical fluid region. So in this case, we look at the minimum discharge temperature is applied. Pressure fluctuations, like I said, result in degassing and oil foaming. But of course, we have to start out with using the correct oil and for the correct application. And sometimes, there could be 3 different oil types approved for that compressor, as is the case with some of the Bitzer CO2 compressors. Maximum discharge temperature is 284 degrees Fahrenheit, 140 degrees C. We don't want to get too high, just like in an HFC system, because you get to a point when you start breaking down your oil, burning up your oil and carbonizing. When you're measuring discharge temperature, by the way, for checking discharge superheat or for the minimum discharge temp, for the maximum discharge temp, always get as close to the service valve as you can, within 3 or 4 inches or so. Make sure you've got good contact and even insulate the sensor. Get a good reading. So here's an example of a compressor, of course, that's operating at fairly low superheat. Discharge superheat in this case is going to be too low, primarily because your suction superheat is coming in too low. And we can see the signs here. So we have a frosting and or wet terminal box here, which can result in premature failure on the electrical front because condensation, any openings in the box at all, where conduit cables come in, things like that, will allow moisture ingress, which can allow for condensation subsequently on the terminals. And then we have arcing and these things can happen. So we should never see a compressor like this at all. Obviously, the minimum crankcase temperatures are not respected. If you look at the end plate here, there's a bearing, okay, in this is a transcritical compressor. There's a bearing behind here. Obviously, the oil is just saturated with refrigerant because the refrigerant is boiling in the compressor and absorbing heat from the compressor casting. So in this case, we know without a doubt here that the bearing is not receiving enough lubrication. This is something I mentioned before about the scenarios that you can run into with the CO2 system. This is, and I apologize, I'm kind of jumping around a little bit. It's really because the transcritical session, I've got a lot of material to cover. So I've kind of shifted some into the subcritical section here. So here's some scenarios you can run into with a booster type system. And a booster type system, although we haven't covered it yet, is basically, it's similar to a cascade system, except that you don't have the cascade heat exchanger, and your low stage and high stages are, they use the same refrigerant. Okay, so that's how that works. Sounds like my security dog is barking out there. So here's a scenario where we have a high medium temperature load and a low temp load. And if these points don't make sense, by the way, I encourage you to tune in on February 16th and I'll clearly explain this in more detail. If you have a high medium temperature load and a low temp load, this will result in a fairly low return gas temperature for the medium temperature compressor. So that may make it hard to achieve the minimum superheat that's required for the medium temp compressor. CO2 systems that of the booster type generally use a flash gas bypass circuit, which vents high pressure vapor from a receiver into the medium temp group. But as it does that, when you have a pressure reduction of the vapor, oftentimes liquid will form. It's very normal to have, say, 1, 2, 3% liquid formation in that bypass, and that's being dumped into the suction line. And you may recall from our last session that one of the challenges with CO2 is that a droplet of liquid leaving the evaporator, for example, has a very high latent heat. In this case, it'll be leaving the receiver. It has a very high latent heat, but generally all these pipes are insulated in the CO2 system. of course, and with a high latent heat, and also the fact that it requires much more pressure drop compared to HFC refrigerants to boil off that droplet of refrigerant, it's safe to say that that refrigerant is going to end up at the medium temp suction. So there needs to be a good source of heat to offset that. So that's where it can be a little more challenging. And fortunately, a lot of systems that run in booster mode like this have a fairly balanced low temp, medium temp, which varies based on ambient customers in the store and that sort of thing. But of course, there can be variations. So this is one of the things that we can run into when you have a high medium temp load and low temp load. And in this case, we can experience very low discharge superheats and problems with our medium temperature circuit. And this is actually a fairly common failure mode with compressors. Oftentimes it'll be a medium temperature compressor and the superheat's running too low. A lot of times this will happen during the system startup where the compressor is compromised right from the start. But what if we had a low medium temp load and a high low temp load? Well, the low temp load is actually discharging warm refrigerant into the medium temp compressor. So if you've got very low medium temp load and lots of warm refrigerant coming from the low temp compressors, now we have a high return gas temperature feeding the medium temp compressors. So just a couple of points to consider. So good capacity control of each suction group, of course, is essential. But also heat exchangers become more important with an with a CO2 system. The internal heat exchangers, such as a liquid to suction heat exchanger in a subcritical circuit, for example, is a great way to exchange heat from your liquid supply to the low temp evaporators and transfer some of that heat into the suction gas to get the return gas temperatures up. And that's an efficient way to do that. And this can be done on the medium temp side, as we'll see on the 16th. So with this slide, what we're looking at is we start out with a subcritical circuit running a fairly low temperature evaporator at minus 32 degrees C. Okay. And in this case, even the discharge or condensation is going to take place subcritically. So we can generally do that with a single stage circuit. If we want to operate a low temp refrigeration system and reject the heat at a temperature such that we will be above the critical point, we have to transcend the critical point, involves transcritical refrigeration. And to do this with a single compressor is going to result in a very high discharge temperatures. And this is of concern. So we do have to be aware of this, but this is our segue into transcritical refrigeration and booster systems and some other configurations that we'll talk about on the 16th of February. So on that note, that concludes the presentation. I'll open up to Matthew in case there's any questions.
Fantastic. Thank you so much. A lot of great information. And we did throw a lot at you, but it will be available also on the video if you want to recap. And you got the email there. I do have a couple questions for you if you got some time. We got about 5 minutes left.
Okay.
Awesome. Let's start with Rana. Hi, are there any additional considerations for CO2-based heat pumps for hot water generation for non-industrial applications like domestic, space heating, comfort applications? Any specific concerns or challenges, as these are usually small capacity systems as compared to commercial industrial systems? A lot to tackle, but
yeah, it is. Depending on what the heat source is, I guess. I mean, CO2 is a very viable refrigerant for heat pump type applications. And I guess as with any refrigerant, you can use it to reject heat. On the high side, one really nice advantage of, in fact, I'm struggling to find a disadvantage here because taking advantage of the heat off of the high side of a CO2 system is very advantageous, especially when you're operating supercritically like this, because the cooling of CO2 on the high side of, say, a heat pump system like this would behave similar to de-superheating. So in other words, as your CO2 is cooling, your hot water or air is heating up. So you've got this, a relatively, I won't say constant temperature difference, but you always have some temperature difference. When we're applying HFC refrigerants to an application like this. Those of you who are familiar with heat reclaim, for example, in supermarkets, whatever your condensing temperature is, that's as cool as you can get. That's basically you've got a certain amount of superheat in that refrigerant, which is so little that you're going to get very little heating effect out of it. So now you might be relying on a 100-degree refrigerant because you could be condensing at 100 degrees Fahrenheit. And that's all you have for heating. With CO2, you can start out at something like 200 plus degrees Fahrenheit, and naturally follow the heating profile of the water or air. So aside from selecting heat exchangers, considering variations of load and things like that, I can't really think of any disadvantages. We always have to be aware of how we're applying the compressor. So make sure that the proper oil is being used. Generally, when you get into the higher temp applications, a special oil is required for the heat pump application like that. So I hope that answers the question.
Thank you so much. I got two more if we've got some time. Can a VFD be used with unloading simultaneously?
No. So the compressors are semi-hermetic, they're refrigerant cooled. So you have the choice, the flexibility is there to use a variable speed drive, or you can use unloading, for example, the variable unloading, which would be the most, that would be the approach for unloading, in fact, with CO2 compressors. If you were to slow the compressor down to the minimum speed of say it's 25 Hertz or something like that, and then you start unloading, we get to a point where we just have so little flow that motor can't be properly cooled. We can run into problems with oil management, things like that. But the bigger thing, I think, is the refrigerant cooling. So use one or the other, mutually exclusive, right? Use one or the other, never both together.
Thank you so much. Maybe a final one, unless people want to add to the Q&A box or the chat. Why are some temperatures listed at degrees K or degrees R and others are not?
And this is something that I've had to get used to myself. Getting on board with Bitzer a number of years ago is I've noticed a lot of literature is expressing temperatures in either degrees Celsius, degrees Fahrenheit, degrees Kelvin, degrees Rankine. So the easy way to remember this: degrees Kelvin and degrees Rankine should be a quick indication that we're talking about a temperature differential. So if you refer to an evaporator temperature, then we're looking at a saturated suction temperature or evaporating temperature, say, of 20 degrees Fahrenheit. And the condensing temperature could be 100 degrees Fahrenheit. When we're talking about the superheat leaving the evaporator, let's say we have a 10-degree Fahrenheit superheat. By saying 10-degree Rankine, we know right away it's a temperature differential. Similarly, if we're measuring subcooling on the high side of a system, which is the difference in temperature between the saturated temperature of the refrigerant, the condenser, minus the liquid temperature, okay, in the liquid line, you would express that in Rankine or Kelvin. And it's not to say that it's incorrect to say superheat, refer to superheat in Fahrenheit or Celsius. It's just a convention that seems to be used more and more. A lot of refrigeration reports and papers and that are written refer to temperatures this way, and that's why it's done.
Do you have time for two more questions? I know we've hit the 1
Sure.
o'clock mark. A couple came in here. Are the transcritical compressors available that can be used in freezing applications as a single stage circuit?
I'm sorry, I missed part of that. Available in a which type of application?
Are the transcritical compressors available that can be used in freezing applications as a single stage circuit?
No. You could, in theory, with Bitzer's approval, we need to know about the application, but you can run a transcritical. In theory, you can run at lower temperatures, but we still have that limitation, whether it's a subcritical compressor or transcritical compressor or any compressor for that matter. Once as your compression ratio increases, your discharge temperatures are increasing and your efficiency of the compressor is getting less and less and less. You're dealing with clearance volumes and rate expansion of gases. And one of the big ones here is that you get to a point where you're heating up the refrigerant so much during the compression process that we reach a point where we start compromising the oil. Oils are going to break down at a certain temperature. Let's just say 300 degrees Fahrenheit, 300 degrees Fahrenheit plus. You start reaching temperatures like that, as you would with, say, running a transcritical compressor that's trying to serve a low temperature evaporator and reject heat supercritically on a 90-degree day, for example. It's just going to be way too hot. It's going to burn up.
Thank you so much. Another oil-related question from Mark Andre. Should we err on the side of higher viscosity oil if multiple options are available?
We should actually look at the application in the operating instructions. For the compressor, it will suggest which oil to use based on the application. So, for example, generally the lower the temperature, lower temp application, you would use the lower viscosity. So you would look at what that temperature range is and choose the oil that's applicable. So it could be the BSE 60K. If it's let's say it's a medium temp single stage transcritical circuit, that would be the BSE 85. So it's a little warmer, that application. So the oil would need to be a little thicker. And when you get into even higher temperature applications like heat pumps and what have you, you'd be into the BSG 68. Now, of course, when you get into booster systems that have a low temperature circuit and a medium temp circuit, booster implying that there is no heat exchanger between the low stage and the high stage. What leaves the low temp compressors is going to end up in the high stage. We can't have two different oils in a system like that, so we have to, go with the best oil. And in that case, it'd be a BSE 85K again. So depends on the applications, but you can find this information in the operating instructions. I always highly recommend go to the operating instructions. There's a lot of information in there, and not even just about the compressor, but system commissioning, these oil types, everything else. So
cool. Last but not least, do you play that guitar that's behind you?
yeah, that's actually one of three. So you want me to go play a song now?
Tell you what, for part 3, that'll be the teaser.
Yeah, you go, part 3. Actually, I haven't played it in a little while, to be honest with you. I'm too busy preparing for webinars for HRAI.
I was going to say, and I think you got more to go to. So we will say goodbye. Please join us again February 16th for part 3. Why do I always stumble on that word? Transcritical compressors. We'll go much more in depth on that. Thank you so much, Phil. This has been a lot of great information and a great resource. The video will be out there if anyone wants to use it.
My pleasure. Thank you, Matthew. Thank you for everyone for attending. Have a good day.
Okay. And thank you all for attending. Cheers. Thank you so much, Phil. Until next time.
Thank you, sir. Take care.